We'll finish up our study into graphs and directed graphs by examining the practical problem of finding the shortest path between two vertices in a graph or digraph that either does or does not have edge or arc weights. So the most basic problem that we want to consider would be, given a graph or given a digraph and given two vertices in that, can we find a path or a directed path to get from the first vertex to the second vertex? And if that is possible, we'd like to discover the shortest possible way to do that. Okay, and I say again, the edges might or might not have weights assigned to them. Let's go ahead and assume that the edges do have weights. If they don't have weights, then we can think of the edge weights as being 1 implicitly. But let's assume we have edge weights, arc weights. Okay, the most popular algorithm by far for solving this problem is called Dijkstra's algorithm. And we're going to learn this algorithm in detail. Okay, I've already said this in the past, but it bears repeating very fast. There's an awful times when graphs are used to represent different sorts of things, and we talk about weights of edges, and we talk about distances of paths, and so on and so forth. But the fact is that what we call the distance of a path might really not reflect a physical distance at all. It really might be something quite different. Like we saw previously with laying cables when we were doing the spanning tree business. The weights on the edges were really about costs to connect cities, right? Okay, so we could be in a situation like that again, where what we're calling distance, when it might not really be distance, okay? It's important to realize just how general the sort of problem we're dealing with here is, okay? We talk about distances between vertices, we talk about lengths of paths, but bear in mind that that might just be an abstraction, okay? Let's start talking about Dijkstra's algorithm. As I mentioned, we're going to apply Dijkstra's algorithm to an edge-weighted graph. We're going to think of the weights of the edges as conveying a sense of distance between vertices along that edge, okay? And paths we'll think of as having lengths, right? The sum of the edge weights along a path will be the length of the path. Okay, we do this regardless of whether the length really conveys the sense of an actual length or something else. So again, if we had an ordinary graph without edge weights, we could treat that as an edge-weighted graph by simply assuming that each edge had weight 1. Okay, throughout our discussion, S and T are going to denote two particular vertices in the graph, and S is going to be the starting vertex for the path that we're trying to find, and T is going to be the vertex that we're trying to get to, okay? We'll work with undirected graphs, but the same reasoning could easily be adapted to achieve a digraph version of Dijkstra's algorithm. Okay, letter S will, well, I guess it stands for start or the source or start vertex, and T stands for the target vertex. The way Dijkstra's algorithm works is by beginning with S, focusing in on S first, and then steadily discovering vertices that are further and further away from S. Okay, so it pretty much radiates out from S. And if the goal is just to get to the vertex T, then the way this is going to work is that by the time we discover vertex T and process it, we'll talk about what that means. By the time we do that, we can be assured that we will have discovered the shortest path from S to T. If we apply Dijkstra's algorithm and never manage to discover the vertex T that we're looking for, but we run out of vertices, then basically it's time to conclude that T is not in the connected component of S. It's not possible to get from S to T. Okay, so that'd be a failed case. Another thing is, we might be interested in trying to find all the shortest paths from the vertex S to every other vertex in its connected component, right? We may not be focused on a particular target vertex T, and Dijkstra's algorithm works just great in that case too. We keep discovering vertices, and as we discover new vertices, we also discover the shortest paths to those vertices. Before getting into the details of the algorithm itself, it's useful to introduce some notation that's commonly used for Dijkstra's algorithm. And some of it is standard graph theory. Given any two vertices u and v in a graph, we can talk about the distance between u and v. And it's simply this: assuming that u and v are in the same connected component, then the distance between u and v would be the length of a shortest possible path that connects u and v, right? So that makes sense. The notation delta parentheses uv parenthesis will be used to note this distance. Okay, again, it's the length of the shortest path that connects u and v. But of course, u and v might not be in the same connected component. There may not be any path from u to v. In that case, we'll say that the distance between them is infinite or infinity, and we'll write delta uv equals infinity. As we approach Dijkstra's algorithm, we want to regard infinity as something meaningful mathematically, and we want to think of it as something that's greater than any actual number. Okay, when we compare infinity to some other distance, if that distance is a finite number, we'll think of infinity as greater than that number. Because we've chosen to discuss Dijkstra's algorithm in the context of directed graphs, well, in a directed graph, the distance from u to v is the same as the distance from v to u, right? Because if you can take a path from u to v, well, you can just reverse that and go from v to u basically along the same path. This would certainly not be the case in a directed graph. Having a path from u to v would have, a directed path from u to v, not say anything about directed paths from v to u. Okay, so now we're going to talk about the notion of the discovered distance from the source vertex S to some vertex v. Okay? As I said earlier, as Dijkstra's algorithm proceeds, there will be more and more vertices discovered. Suppose v has been discovered. Okay? Well, then we'll have a sense of a shortest path to get from S to v, but not necessarily the shortest path in the entire graph. It's only shortest sense of shortest among the paths that have been discovered so far. You'll see this as we go, okay? So delta S comma V, delta S comma V, what does delta S comma V mean? It means the actual shortest distance from S to V, right? Among all the possible paths in the graph, we'd be thinking about the shortest possible path, and the length of that path would be delta S comma V. In contrast, we're going to use this kind of funny notation V dot D. And V dot D is going to be sort of similar to delta S comma V, because it is going to record a distance to get from S to V, okay? A distance to get from the source vertex S to this discovered vertex V. But it's only going to be the distance along a shortest discovered path, right? We're only considering paths that have been discovered. The algorithm doesn't know about the entire graph, and it may be that at some moment the shortest discovered path from S to V is not the true shortest path, because the true shortest path would involve some vertices that have yet to be discovered. In fact, initially, what we'll do is we'll set V dot D to infinity for every vertex except for S. We're going to set S dot D, we'll set that to 0, okay? This takes no distance to get from S to itself, so S dot D is 0. But initially, and the notation is admittedly a little bit awkward, but somewhat standard. Okay, but for every other vertex V dot D is infinity, because in the beginning, we don't know any way to get from S to V. All right, as the algorithm proceeds, if you can get your head around this inequality right here, then you understand the notation. Yeah, because at any stage along the way, for any vertex V, it's always going to be true that V dot D is greater than or equal to delta S comma V. Okay? So like it or not, this is just funny notation for saying that the shortest distance to get from S to D along discovered paths is greater than or equal to the shortest distance to get from S to V along every path. You can consider every path in the graph in that case. Okay? So I say it once again because this may not have resonated, and it's absolutely cool that you get your head around this idea. Delta S comma V is the true shortest distance from S to V in the graph, whereas V dot D is the shortest distance along where we restrict only to paths that have been discovered so far. And here's a very critical observation, something that certainly should be proved, but we won't prove it. But it's a very basic, important fact about Dijkstra's algorithm, and that is that Dijkstra's algorithm involves this notion of discovering vertices and also processing vertices. And when you get to a vertex and it's time to so-called process that vertex V, at that moment, it'll be guaranteed that V dot D is equal to delta S comma V. In other words, it'll be guaranteed that we will have discovered by that time a shortest path from S to V. Some other funny notation. So what we're going to do is we're going to let V dot pi denote another vertex in the graph. Okay? At the time when we are ready to process the vertex V, not only will we have discovered a shortest path from S to V, but we will have recorded which vertex comes immediately before V along that path. Okay? So whatever vertex V dot pi is, that vertex is the vertex that comes immediately before V along a shortest path from S to V. Okay? So there is an edge connecting V dot pi to V. The pi here stands for previous. As Dijkstra's algorithm proceeds, at any given moment, any given vertex will be in one of 4 possible states. The vertex might be undiscovered, okay? So undiscovered vertex is simply a vertex that the algorithm has not dealt with in any way. It basically hasn't even been noticed, really, okay? When I draw some diagrams of graphs, when I represent the graphs to convey a sense of Dijkstra's algorithm, I will draw undiscovered vertices. I will make them white. Okay, or a vertex might be discovered, so it's at least been noticed by the algorithm. And such vertices, I'll draw them gray in my diagram. After a vertex is discovered, it might later on be processed, okay? Or we also say visited. So visited and processed really mean the same thing here, okay? Once a vertex has been processed, I'm going to represent it in the graph as a black vertex. Okay, and I'll also represent exactly one vertex will be yellow, and that will be the quote-unquote current vertex, meaning that's the vertex that is currently being processed, the one that's currently being visited. Okay, I say again, at any given moment, exactly one vertex will be processed, will currently be being processed. Let's talk now about how a vertex comes to be discovered, how a vertex goes from the undiscovered state to the discovered state. And this is really quite simple. While visiting another vertex, there may be an edge from that visited vertex to an undiscovered vertex. And if there is, then that vertex will become discovered. Okay? I don't think I said that particularly well. So once you start processing a vertex, all of the undiscovered neighbors of that vertex will become discovered. In a little while, we're going to worry about a really critical issue, namely, which order should the vertices be processed? Okay, in what order should the vertices be processed? This is the source of a lot of mistakes that people make when learning Dijkstra's algorithm. Okay, it really is a critical issue to process these vertices in the correct order. Here's what has to happen while visiting a vertex V, okay, while processing a vertex V. By the time V is processed, if the algorithm has been carried out correctly, by the time it's V to be processed, it's pretty much a guarantee, it is a guarantee, that V dot D will equal delta SV. Okay, now think about this. V dot D is something that changes as the algorithm proceeds, right? Initially, V dot D is infinity. We started with V dot D equal infinity. And V dot D will change at different stages along the way. Though that it's time to process V, the vertex V, it's guaranteed that V dot D will equal delta SV. V dot D will be now the true distance from S to V. Okay? And it will also be the case that V dot pi will be the vertex that comes right before V along a shortest path from S to V, as I previously said. You have to trust that that works. Okay? Now, while processing V, it's necessary to consider all of the neighbors of V, all of the vertices that are adjacent to V. For each of these neighbors, let's call a neighbor U. U is a neighbor of V. So what do we have to do? We're visiting V, and we have just noticed U. What has to be done? Okay, well let's see what this says we have to do. If U has already been processed, that is visited, then we can safely ignore it. Okay? Yeah, okay. There's no need to do anything with U if it's already been processed. Okay? But, and I should have put a but here, if U has not been processed yet, then consider the weight of the edge that connects V to U. Let's let WV comma U denote the weight of the edge connecting V to U. And what we have to do now is check to see whether or not V dot D plus WVU is less than U dot D. Let me explain that inequality in more human terms, right? What we're checking is to see if the discovered distance from S to V plus the weight of the edge in V to U is less than the discovered distance from S to U. Okay? Now think about that for a second. Suppose that's true. We're saying that there's a way to get from S to V and then use this edge that goes from V to U, and the total distance of that, which would be from S to U, is actually less than the currently discovered distance from S to U. Okay, well that's a big deal. If that's true, that's a big deal because it would mean that we just discovered a shorter way to get from S to U. Right? Think about that. The only way that inequality can be true is that we discovered a shorter way to get from S to U. How? Well, use the shortest path that we know so far to get from S to V, and then follow the edge from V to U, and that will be shorter than any other path from S to U that had previously been discovered. Okay, so that's a big deal. We just found a shorter path. All right, well, it's time to reflect the fact that we now know a shorter path. So first thing, let's change what U dot D equals, right? Let's set U dot D equal to V dot D plus WVU. Okay, in other words, U dot D now becomes the length of this shortest path that we've so far discovered from S to U. Okay? And let's also keep track of the fact that the vertex V that's currently being processed would be the next to the last vertex along this path from S to U. Right? V would come immediately before U along a shortest path from S to U. Shortest in terms of shortest of among the paths discovered so far. I hope you get that. I mean, you really have to think about that. That there is the critical idea of Dijkstra's algorithm. Okay? By using this information, V dot D and so forth, we're able to notice when we've found a path that's shorter than any other path that we've seen so far.